Okay, hi guys. Welcome to Biophysics class 32. And we're going to continue to look at the diffusion of ions across cell membranes in anticipation of our study of the nerve impulse and the action potential at the end of the semester. And in this class, actually the next two classes, we're going to look at something called the GHK equation, standing for Goldman-Hodgkin's-Katz equation, which is a little bit more detailed model of ion transmission across membranes than we achieved in the last class with the Donnan equilibrium. But first, let's do a brief review of what we learned last class, the Nernst potential and the Donnan equilibrium, just to refresh our memories and to remind ourselves where the Donnan equilibrium succeeds and where it falls short. So the Nernst potential was the voltage difference required to maintain a given concentration difference for an ion across a cell membrane against the ion's natural tendency to diffuse. And it was given by this equation. The Nernst potential was kBt over the charge on the ion times the log of the concentration outside the cell over the concentration inside the cell. So just for example, for these K plus ions here, if it was just diffusion, they would tend to, diffuse from the inside to the outside of the cell. But because there's a membrane potential, which is negative inside the cell, there's an electrical force back which counters that diffusion. And if that electrical voltage is equal to the Nernst potential given above, then the diffusive and the electrical tendencies cancel. So Donnan equilibrium was applying the Nernst potential given ion concentrations like K plus and Cl minus and Na plus, which is not shown here, outside the cell, assuming cell neutrality, as well as the concentration of trapped macromolecules like proteins inside the cell. So those were the givens. And then in several equations requiring charge neutrality inside the cell, so the concentrations of the different ions inside the cell should add to a net zero charge, and that the membrane potential should equal the Nernst potential for each ion, so that the ion flow would be balanced and in equilibrium. So we then in the Donnan equilibrium that gives for three ions, that gives four equations in four unknowns, the free ion concentrations inside and the membrane potential, so we can solve for the membrane potential and the ion concentrations inside the cell. So that sounds good. And there were pros to the Donnan equilibrium. We've found a membrane potential of about minus 10 millivolts, which is the same sign and the same order of magnitude as the measured cell membrane potentials of minus 60 millivolts. However, there were some cons to the Donnan equilibrium, which were that the total concentration inside was larger. So there were more ions inside, a total concentration inside, leading to an osmotic pressure that could burst the cell. But more importantly, it's possible to measure Nernst potentials for each type of ions experimentally. And in cells, they don't match each other, and they don't match the membrane potential of minus 60 millivolts. So it appears that ion flow is not a completely equilibrium process. That is, it isn't governed only by setting the chemical potentials on both sides equal and balancing the effect of the electrical force and the diffusive force. It appears that something else is going on And that something is ion pumps. So active transport of ions back and forth across using ATP energy. So here's a little pump here with some suggested ions. So taking into account the action of ion pumps is the GHK, or Goldman-Hodgkins-Katz equation. And so here's a picture with all three ions, Na, Cl, and K, potassium, on the outside and on the inside of the cell, along with some macromolecules, which are labeled A here. But here we have an ion pump, which serves to proactively pump a given type of ion, in this case potassium. This would be a potassium pump across the membrane, expending energy from ATP molecules. So the effect of the ion pumps can be simulated by assigning a different permeability to each type of ion. And this permeability reflects the net ability of each ion to diffuse through the cell membrane, including its natural diffusion and the effect of these ion pumps. So this leads, including the permeabilities, as you'll see in a second, leads to a generalization of the Nernst equation called the GHK equation, or sometimes just the Goldman equation after the G for Goldman. And this is what it looks like. It says the membrane potential across the cell membrane is RT over F times the natural log of the permeability of the first ion times the concentration outside, plus the permeability of the next ion times the concentration outside, plus the permeability of the third ion, Cl. Notice that this is times the concentration inside for the negative Cl. So we'll think about that in a second, why that might be true. But first, again, these are the permeabilities of the different ions, okay? They each have their own permeability, which is determined by how well they can get through the membrane and how many pumps of different types act on them. And just to familiarize yourself with these constants, R is the ideal gas constant used in chemistry, and F is called Faraday's constant. It's the electric charge that is stored in a mole's worth of electrons. Okay. Now it turns out that R over F here is equal to Boltzmann's constant over the elementary charge. And we'll actually work on this in an exercising class just to make sure we're clear on the units. So let's see the limiting cases here. Without the potassium and chlorine ions present, so if these concentrations here for potassium and chlorine are 0, we get the membrane potential is RT over F times the log of the permeability of sodium times the concentration of sodium outside over the permeability of sodium times the concentration of sodium inside. But now noting that what I just claimed, that R over F is KB over the elementary charge, this would be KB over E. R over F becomes KB over E times the log of, and then these permeabilities cancel out. So we just have KBT over E, and E, the elementary charge, is the charge Q on the sodium ion times Na, sodium concentration outside over inside. And that's the Nernst potential for Na. So that's why this is a generalization of the Nernst equation, because if we ignore all ions except one, we get the equation for the Nernst potential. That is, we get that the membrane potential would be equal to the Nernst potential for that ion. And then here's the question, why are the concentrations for chlorine flipped here? That is, for sodium and potassium, we have out on top and in on the bottom, whereas for chlorine, we have in on top and out on the bottom. Well, if we look here, if we ignore sodium and potassium, we get delta V, the membrane potential is kBt over E times log of Cl in over Cl out. But notice that the charge on this is not the charge on the chlorine ion. This is a positive number. We need a negative number here. So we can use the rules of logs and view this as chlorine out over chlorine in to the -1 power and bring a negative out in front. And so we get kBt over E minus E times the log of chlorine outside over chlorine inside. And so we then have kBt over the charge Q on the chlorine ion times outside over inside. So the reason that this is flipped is because the charge of the ion is negative, and we need the log to flip to get the correct charge out in front. Okay, so so what have we done? We've reviewed the Nernst potential and the Donnan equilibrium, and reminded ourselves of the limitations of the Donnan equilibrium. We've seen that there are these ion pumps which affect the permeability of different ions, and we've seen a generalization of the Nernst equation, the Goldman equation, or the GHK equation, which takes into account the ion pumps and the differing permeabilities. And so in class, we're going to be, as I said, verifying these units and also exploring how this GHK equation, what it predicts for the membrane potential in a couple of cases, and whether it predicts what Nernst potentials it predicts for different ions. Okay, so thanks for your attention, and I will see you in class.